Rules for series and parallel circuits. Here are your priming questions. The first two you should be able to answer directly from the video, and the third is what I want you to think about. Series. There is one path for the electricity or the electrons to flow through. Since there's only one path, what this should tell you is that there is only going to be one current throughout the entire circuit. So whatever speed it's going through in the first resistor is how fast it's going in the second resistor, third resistor, and so forth. So the current is the same. Now the voltage, the total voltage drop across each of the resistors is going to be equal to the total voltage. So if you have your batteries, that's going to be your total voltage, and then you have individual resistors, the voltage at each individual resistor will add up to the total voltage. Okay. Hopefully you saw this in the labs that we've been doing. And with the resistance, you also add up the resistance. So the total resistance equals the sum of all the resistors. And this is for a series circuit. For parallel, this is a bit different. Hopefully from the previous lab you've noticed something at least about the voltage, and the voltage should have been the same for each of the branches. It might have varied a little bit, but it should have been very close to being the same. Now, the current, though, is going to be different for every branch if there is a different resistance in each branch. The sum of the current in each of those elements or those branches will be equal to the total current. So for the current, you add the current in each branch or in each element, and that'll be the total current. The voltage is going to be the same. The resistance here is where things are going to be a bit different. And so this is going to be an inverse addition, at least that's what I call it. So 1 over the total resistance is equal to 1 over the first resistor plus 1 over the second resistor, and so forth. What this should tell you when you look at this equation is that the total resistance is less than the smallest resistor. This is the way for you to check your work with parallel circuits and with the resistance. If you ever calculate the total resistance to be greater than the smallest resistor, you've done something wrong and you need to go back and check your work. So this is how we find the resistance, the total resistance in a parallel circuit. And the reason for this is even though you might have some high resistance and some low resistance, there will always be some current going through the high resistance as well as the lower resistance. And so the total resistance equivalent is going to be less. You'll see this much more in practice as we are doing our problems and as well as when you're building your own circuits. Now, complex circuits are a combination of series and parallel. When we are working with complex circuits, which is not part of this video, you will need to be able to identify parts of a complex circuit that are series or parallel and combine them to find what we call the equivalent resistance. So these rules will be the same for complex circuits, but it'll only be for part of a complex circuit. And this is a very quick table that I personally use when I think of the rules for series and parallel circuits. So for series, the voltages add to the total, the current is the same, the resistance adds. For parallel, the voltage is the same, you add the current, and for the resistance, you do that inverse addition. So if you keep this table in mind, it will help you when you're doing your calculations. You should be familiar with these symbols by now: switches, wires, voltmeter, ammeter, lamp. There are a number of different ways of writing out lamps. I typically default to the shorthand using the circle with the cursive L. Resistors, you will be drawing a lot of. Batteries, you can represent as many batteries or whatever voltage with just this one symbol for me, and that'll be fine. You won't be working with these too much with the motor, with the speaker, and ohm meter just measures the resistance, and then we've talked about fuses a little bit as well. The motor simply converts from electrical energy into mechanical, and the speaker converts from electrical energy into sound energy, into sound pressure. So let me quickly show you series circuits. You've probably already built these and are familiar, but I just want to quickly go back through these. So the first thing that you can notice is that there is only one path for electricity to flow through, and you need to add a battery, and you should always add a switch in real life for safety. And when you click on the switch, you have a current, and that's what's shown with these arrows as they flow through. So again, there's only one path for the electricity to flow through. For a parallel circuit, you can see with the way the wires are set up that there are multiple paths for the electricity to flow through. And if we do the same thing, and we have our switch, we have our battery, and we have our light bulbs, we can put one on each branch. And when we click on the switch and turn it on, what you should notice is that the electricity, the electrons, they split as they go from one branch to the next. This is parallel. And this is when you have only a single resistor on each branch or element, however you want to call it. So, some calculations. I'm going to show you how to do the first one for series and parallel, and then you'll want to pause and work on the second one for both series and parallel. These are what you're going to be checking in class with your neighbor. All right, so series circuit. We can see that there is a single path. We have a battery that has 75 volts. We have two resistors, and we have an ammeter that's measuring 3 amps. So the first thing that you want to do is when you're trying to analyze the circuit is you go ahead and list out what you have in the table. You'll see the table at the bottom, and you want to go ahead and list whatever you are given, whatever you have. And so for here, we're given our battery voltage, which is going to be our total voltage. So we know that's going to be 75 volts. We're given our current from the battery, so that's going to be 3 amps. We're given our R1 as 5 ohms. And once you've filled in all that is given to you directly in the circuit, now you need to go back to the rules, and you need to think back to Ohm's law, V equals IR. And so one of the easiest things for series circuits is the current. The current is going to be the same through all of these. So if we know our total current is 3 amps, we know our I2 and our I1 are both 3 amps. And with the way I've set up the table here, VIR, it matches the way I'd write out Ohm's law over here as V equals IR. So anytime you have 2 out of the 3 in a row, you can find the third. So if we have 3 amps and 5 ohms, we know that we have 15 volts across our first resistor over here. So that's going to be 15 volts over here. And when we look at this now, we think back to the rules for series, and the voltages add up to the total. So V1 plus V2 equals VT. So 15 plus V2 is equal to 75, which means that our V2 is going to be equal to 60. So V2 is equal to 60 volts. So V2 is 60 volts. And now that we have this, we have 2 out of 3 for both of these rows. And we know V equals IR, so 60 is going to be equal to 3R2, so that's going to be the R2 over here, which means that our R2 is going to be equal to 20 ohms. And now we can actually solve our RT in 2 ways. We can go across using V equals IR, and we can also add up our resistors, our R1, R2, to get our R total, and that is from the rule for series circuits with resistance. This is actually one way for you to check your work with simple circuits for both series and parallel when we get to parallel, in that with the rules, you can check your work very easily. So this should be equal to 25 ohms in both directions, if that makes sense. So V equals IR, 75 divided by 3 will give you 25, and then you add up the resistances, so 5 plus 20 gives you 25. You can pause the video now, draw this out, and fill in this table so that you can check with the people around you in class. We're going to go and move on to parallel circuits for this video though. So parallel circuits. You can see that there are many branches here where the electrons will split off. So this is going to be a parallel circuit, and this is a simple parallel circuit because there is a single resistor on each branch. If there were multiple resistors on each branch, or even on one branch, this would be a complex circuit, which we will address in the next video. So again, we look at our circuit and we begin to list out what we are given. So R1, 6 ohms, R2, 12 ohms, R3 is 4 ohms. So looking at this already, and we are also told that our total current is 3 amps, but with what we just filled out, we have R1, R2, and R3, so we can find our total resistance, our RT. Now this is the inverse addition. So 1 over RT is equal to 1 over 6 plus 1 over 12 plus 1 over 4. And what you should get for this is 1 over RT is equal to 0.5, which means that our total resistance is equal to 2 ohms. And remember, the total resistance for a simple parallel circuit should always be less than the smallest resistor. We look at here 4, 12, and 6, and we have a total of 2, so we are good. So 2 ohms for the total resistance. And now we have 2 out of the 3 in the row, so we again use V equals IR. And so we do 3 times 2, so VT is equal to the current, 3 times the resistance of 2, which gives us a total voltage of 6 volts. So we know our total voltage is 6 volts. And going back to the rules for parallel circuits, we know that the voltage is going to be the same across all of the branches. So once we know our total voltage is 6 volts, we know all of the other voltages here are 6 volts for each of these branches. And once we have that, we have 2 out of the 3 in the row, and we can begin using V equals IR once again to solve for the currents. So in this case, our current is going to be 1 amp. Our current is going to be 0.5 amps, and our current is going to be 1.5 amps going across. And we can check our work with the current because of the rule for current in parallel circuits. The current 1, 2, and 3 should add up to the total current IT. So 1 plus 1.5 gives 1.5. 1.5 plus 1.5 gives us 3 amps. So that's the way we can check our work. And again, you need to work on this one for practice and check in class.